4.3 Area and Definite Integrals. Southwestern College, Professor Maria Olivas. Area and Definite Integrals. Objectives. Find the area under the graph of a non-negative function over a given closed interval. Evaluate a definite integral. Solve applied problems involving definite integrals. Let's begin with a recap. Let's start off by talking about the indefinite integral. So the indefinite integral is basically the integral of lowercase f of x dx, which is equal to uppercase f of x. And don't forget that plus c. So remember, we introduced this notation of the uppercase f of x, and this represents the antiderivative basically of lowercase f of x. And we introduced this notation in section 4.1 on anti-differentiation. So this is what we started learning when we started our chapter on chapter 4. And then we moved on to 4.2, which was on the definite integral, the integral from a to b of lowercase f of x dx, which actually represents a net area. And I'm going to go ahead and draw a little sketch of a graph so you have a visual here to accompany this. Let's go ahead and draw a coordinate plane, but let's just focus in here on quadrant 1. I'm going to draw a little curve here, and we're going to point an arrow at it, and we're going to call this lowercase f of x. I'm going to draw lines going down from this curve, and I'm going to call this value of x here value a, and then I'm going to call this other value of x here b, and I'm going to shade in under the curve all the way down to the x-axis in between the interval a and b. So this was section 4.2, where we found out how to find that net area using a definite integral. Now the fundamental theorem of calculus is going to be the integral from a to b of lowercase f of x dx, and this is going to be equal to the antiderivative of f of x, which is capital f of x, and this is going to be evaluated from a to b, which will equal uppercase f of b minus uppercase f of a. So that's basically the antiderivative of f of x evaluated at b minus the antiderivative of f of x evaluated at a. I'm going to go ahead and box that in because that's pretty important. I'm also going to go ahead and draw a little red star above it, and I'm going to write down the word memorize right above it with an exclamation point. Steps to using the fundamental theorem of calculus to evaluate definite integrals. And here we have the general form of a definite integral, the integral from a to b of lowercase f of x dx. Number 1, find the antiderivative function for lowercase f. And this basically means find uppercase f of x, right? So that's what we've been using. We've been using that notation to represent the antiderivative function for lowercase f. Number 2, evaluate the antiderivative function first at x equal to b and then at x equals a, and subtract your results. And I'm drawing a cloud around subtract your results and an arrow pointing up to the fundamental theorem of calculus where it says capital F of b minus capital F of a. And I'm going to rewrite it here under the 2 where it says capital F of b minus capital F of a. Example 1. Evaluate each definite integral. A. So for this example, we have the integral from 2 to 5 of the quantity 2x plus 3 dx. This is going to be equal to, first we're going to find the antiderivative of 2x plus 3, which will be 2x squared all over 2, plus 3x plus c, and I'm going to do that plus c in a different color. I'm going to do it in blue because I want to refer to it right now. And this will all be evaluated from 2 to 5. So now that we found the antiderivative, we are ready to do the second part, which is we're going to subtract our results, right? Where we find, where we use the antiderivative evaluated at b minus the antiderivative evaluated at a. So here I'm going to simplify first. So first I'm going to write the antiderivative simplified, which is going to be equal to x squared plus 3x plus c, and then this is going to be evaluated from 2 to 5. Now I'm going to go ahead and substitute first the 5, which is the upper limit. So this will be 5 squared plus 3 times 5 plus c, all inside of a set of parentheses, minus, open up a set of parentheses, 2 squared plus 3 times 2 plus c, close the parentheses. And here you can see that this minus sign is going to be distributed. And when you distribute this minus sign to the c that's at the very back, where it says plus c, and then the c in the first expression, you can see that these c's are going to basically cancel each other out. So in reality, this is going to happen every single time you find a definite integral. So we don't necessarily have to write this plus c at the end here when we're finding a definite integral. Okay, now this equals, open up a set of parentheses, 25 plus 15, close the parentheses, minus, open up a set of parentheses, 4 plus 6, close the parentheses. This is going to equal 40 minus 10, which is equal to 30. And let's go ahead and box in that final answer. On the right-hand side, I am going to draw a sketch of this graph and the area it represents. So here is a coordinate plane focusing on quadrant 1 with the line y equals 2x plus 3. Here's the x values from 2 to 5. I'm going to label the line as f of x equals 2x plus 3. I'm going to shade beneath the line all the way down to the x-axis in between that closed interval from 2 to 5. The y value associated with the x value of 2 is going to be 7, and the y value associated with the x value of 5 is 13. So we would use the geometric formula for finding the area of a trapezoid, which would be area is equal to 1/2 times 3, the height, times the quantity 7 plus 13. And this area is going to be equal to 1/2 times 3 times 20. And this will simplify to a equals 60 divided by 2, which is equal to 30. So the area is going to be 30 square units, which is exactly the same numeric value that I was able to get over here using the definite integral. So yes, this works. All right, example B. The integral from -1 to 3 of 6x squared minus 4x plus 1 dx. This is going to be equal to, first we're going to find the antiderivative, so that's going to be 6x cubed over 3 minus 4x squared over 2 plus x evaluated from -1 to 3. Let's go ahead and simplify this antiderivative before we evaluate it. So the 6x cubed over 3 will simplify to 2x cubed minus 2x squared plus x evaluated from -1 to 3. Now we're ready to evaluate this. So starting with the 3, we're going to have open parentheses 2 times 3 cubed minus 2 times 3 squared plus 3. Close the parentheses. Here we have minus, open up a set of parentheses, 2 times -1 cubed minus 2 times -1 squared plus -1. And then close the set of parentheses. So let's go ahead and simplify this. This is going to be equal to, open up a set of parentheses, we're going to have 2 times 27 minus 2 times 9 plus 3. And close the parentheses, minus, open up a set of parentheses, 2 times -1 minus 2 times 1. And then this, I'm just going to write this as -1 and then close the parentheses. And then this is going to be equal to, open up a set of parentheses, 54 minus 18 plus 3, close the parentheses, minus, open up a set of parentheses, -2 minus 2 minus 1, and close the parentheses. And this will be equal to 54 minus 18 plus 3 will all simplify to the number 39. And then we're going to have minus a -5 equals 39 plus 5, which is equal to 44. And we're going to go ahead and box in that final answer. All right, let's go on to our next example, example C. So this is going to be the integral from 0 to 3 of 4x plus e raised to the x power dx. So this is going to be equal to, first we're going to take the antiderivative and we're going to get 4x squared all over 2 plus the integral of e to the x is just e to the x, and this will be evaluated from 0 to 3. This is going to be equal to, we can simplify that 4x squared over 2 as 2x squared, and then we can just write plus e to the x power, and this will be evaluated from 0 to 3. All right, so we're going to go ahead and evaluate this antiderivative at 3 first, and then we will subtract what this antiderivative is evaluated at 0. So it's going to be equal to, open the set of parentheses, 2 times 3 raised to the second power plus e raised to the third power, close the parentheses, minus, we're going to have open set of parentheses, 2 times 0 squared plus e raised to the 0 power, close the parentheses. And this will be equal to, let's go ahead and open a set of parentheses, 2 times 9 plus e raised to the third power, close the parentheses, minus, open a set of parentheses, 2 times 0, which is just 0, and this will give me, and plus e to the 0 power, e to the 0 is just 1, so we'll just write plus 1 and close the parentheses. So this is going to be equal to, open a set of parentheses, 18 plus e raised to the third power, close the parentheses, minus 1. And this will then equal 17 plus e raised to the third power, and that will be our final answer. We're going to go ahead and box that answer in, and we're done with that problem. So now we're ready to move on to our next example. Example D, the integral from 1 to 2 of 1 over x dx. Let's begin by taking the antiderivative of 1 over x dx. That's going to be the natural log of the absolute value of x, and we are going to evaluate this from 1 to 2. This will equal the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. So let's go ahead and simplify this. This is equal to natural log of 2 minus the natural log of 1. But the natural log of 1 is just 0, so we're going to write the natural log of 2 minus 0, which is just equal to the natural log of 2. And we're going to box that in as our final answer. Okay, example E. Find the area of the region bounded by the graph of y equals x squared plus 1. The vertical lines x equals -2 and x equals 3, and the x-axis. Let's begin by drawing a sketch here of this region. I'm going to draw a coordinate plane here, and this is, once again, this is a sketch. So this is going to represent my horizontal axis, or my x-axis right here, this horizontal line. And now I'm going to draw a vertical axis to represent the y-axis. I'm focusing in here on quadrant 1 and 2. I'm drawing a parabola that opens upward to represent y equals x squared plus 1. I am going to go ahead and label this graph with the equation f of x equals x squared plus 1. I'm also going to draw little tick marks here on the x-axis that are separated by a scale of 1. I am going to label here x equal to -2 and draw a line segment here connecting to the parabola going upwards. And I'm also going to draw here a line segment at x equals 3 going upwards to the parabola so I can enclose the region of the area I'm looking for. I'm going to highlight in yellow the region bounded by the graph of f of x equals x squared plus 1, the x-axis, and the vertical lines x equals -2 and x equals 3. So I'm going to go ahead and move the equation that I wrote here where it says f of x equals x squared plus 1 towards the inside of the parabola and make it a little bit smaller just to make a little bit more space for me to write. I'm going to write A for area. A equals the integral from -2 to 3 of x squared plus 1 dx. And this is going to be equal to x raised to the 3rd power divided by 3 plus x evaluated from -2 to 3. And this equals open parenthesis 3 raised to the 3rd power over 3 plus 3, close the parenthesis, minus open parenthesis, -2 raised to the 3rd power over 3 plus -2, and close our parenthesis. And this will be equal to, open parenthesis, 27 divided by 3 plus 3, close parenthesis, minus -8 divided by 3 minus 2. And I'm going to write that as 2 over 1, and then I'm going to multiply by 3 to the numerator and denominator in order to get a common denominator. And then I'm going to close that parenthesis. And the next line here, it equals open parenthesis 9 plus 3, close parenthesis, minus open parenthesis -8 divided by 3 minus 6 over 3, close parenthesis. And then this will equal 12 minus, and here we will have -8 minus 6 which will give me -14 And this will equal 12 plus 14 I'm going to go back to that 12 and write a 1 under it and multiply by 3 to the numerator and denominator to get a common denominator. And then this was all going to equal 36 plus 14 all over 3, which will simplify to 50 over 3. And then we will box that in. That will be our final answer for that problem. Reminder, the definite integral gives us net area, not total area. Example 2. The picture shows the areas of the shaded regions. Right now the regions aren't shaded, but I will shade them as I do the problem. Find the value of each integral. Before we do these integrals, let me describe the picture that we have to the right-hand side of the screen. We have a coordinate plane that is focused in quadrant 1 and quadrant 4. There is a function with 4 intercepts. The function starts at the x-intercept of a, 0. It increases, it hits a maximum in quadrant 1, and then it decreases and crosses at the x-intercept of b comma 0. It continues decreasing, and then it hits a minimum in quadrant 4. It starts increasing, and it crosses at the x-intercept of c comma 0. It continues increasing, and then it hits a maximum in quadrant 1. And then it starts decreasing, and it stops at the x-intercept of d comma 0. The region bounded by the function and the x-axis between the closed interval of a and b has an area of 5. This area is above the x-axis. The region bounded by the function and the x-axis between the closed interval of b and c has an area of 8, and this area is below the x-axis. And the region bounded by the function and the x-axis between the closed interval c and d has an area of 6 and is above the x-axis. All right, now we are ready to start off with our first integral. So going back here to example 2i, the first integral states the integral from a to b of f of x dx. So here in this integral, our integrand is the f of x. So it is referring to the function that we have on the right-hand side of the screen in this graph. In order to find the area, we need to first identify our limits of integration. I'm going to highlight those in yellow, starting with the lower limit of a. So I'm going to highlight the lower limit a in yellow first, and then b, our upper limit. I'm going to highlight a and b on the x-axis over here in our graph, and I'm also going to highlight the area that's bounded by the function and the x-axis in between a and b. It's a 5, and it's above the x-axis, therefore it's a positive 5. So we're going to write that this integral is equal to 5. We're going to box that in. Going on to the next problem here, the integral from b to c of f of x dx. I went ahead and I highlighted those limits of integration for this problem in green. And I also highlighted the value of b and c on the x-axis in green, and I am highlighting the corresponding area that's bounded by the x-axis and the function between those values of b and c in green. That value is 8, but because it's below the x-axis, it's going to be a negative 8. So I'm going to say that this integral is equal to negative 8, and I'm going to box that value in for our answer. All right, the next problem, the integral from a to c of f of x dx. So a to c, this time, we're going to have to combine two of these shaded regions together because we're starting from A. I'm going to highlight the A this time in blue and the C in blue as well so you can see this interval. So I highlighted those limits of integration in blue, and I highlighted the values of A and C also in blue on the graph. So if we combine these two shaded regions, the 5, which is a positive 5 because it's above the x-axis, and the 8, and that's a negative 8 because it's below the x-axis, 5 minus 8 is going to be giving me a negative 3. So my answer for this integral is going to be a negative 3 because remember that the definite integral gives us net area, not total area. Next example is the integral from a to d of f of x dx. I'm going to highlight those limits of integration in yellow, and I'm going to go ahead over here and highlight the a and d on the x-axis here in yellow, and the area that says 6 that's bounded by the function and the x-axis between the intervals c and d in yellow as well. We're going to have to add up all of these shaded regions now. So I'm going to have to add up 5. I'm going to put 5 minus 8 plus 6. So 5 minus 8 is going to give me a negative 3, and then negative 3 plus 6 is going to give me a positive 3. So the answer for this integral is positive 3. We're going to box that in. Our next example says the integral from d to a of f of x dx. Well, notice that the limits of integration from the problem that we just did here are just switched. So in that case, if we switch the limits of integration, integrating instead from d to a, this will be the same as the first integral we did here, but negative. This is because we are integrating in the opposite direction. So what we have to do is we have to just take the answer that we got here from our prior example, which was 3, and we just basically need to get the opposite sign on that value. So the opposite of a positive 3 is going to be a negative 3. So I'm going to just write here it equals negative 3, and I'm going to box that in. Applications. As we discussed already, the definite integral of a rate of change function gives the net change in the function. For example, given the rate of change function for population, the definite integral will give the net change in population. Given the rate of change function for cost, the definite integral will give the net change in cost. Example 3. Explain what the shaded area represents. So for example 3a, here we see the graph of an increasing function that is concave up in quadrant 1. The area bounded by the function and the x-axis between the interval from 0 to t is shaded in orange. The units on the y-axis are labeled as number of orders per hour, and the x-axis is labeled as time, and in parentheses it says in hours. In order to find the units of the shaded region, it is necessary to multiply the units of the y-axis with the units of the x-axis. So here what we're going to have to do is we're going to have to set up a multiplication problem. I'm going to write these as two fractions being multiplied together. The first fraction is going to represent the units of the y-axis. So where it says number of orders per hour, I'm going to write that as a fraction. We're going to write number of orders in the numerator, and then I'm going to put that over hours, because it says per hour, and the word per means division, so that's why we're going to put the hours in the denominator. And then I'm going to multiply that with the second fraction, which will be in hours. So I will write hours over 1. Before I write that, let me first label here where 0 is on the coordinate plane here. And this is, I circled the t, and I wrote an arrow pointing towards it with a T just in case you couldn't see the T. And then I've circled the number of orders per hour on the y-axis, and then I've circled the time in hours on the x-axis, because that's what we need to know in order to write our multiplication problem here. Okay, so I think now we're ready to set this up. So let's go ahead and set this up. For our first fraction, we had already stated that we're going to write that it's going to be number of orders in the numerator. So let's go ahead and write number of orders. And that's going to be over hour, because that represents number of orders per hour. And then we're going to multiply that with hours over 1. Here, the hours will cross cancel. So we can cancel those out, and then we'll be left with just number of orders. So I'm going to go ahead and shade or stripe the orange region, the part that we're finding, and that part is actually going to represent the total number of orders from t equal to 0 to time t. I'm going to go ahead and box that answer in. Here, for example 3b, we see the graph of an increasing function concave up in quadrant 1. The area bounded by the function and the x-axis between the interval from 0 to 5 is shaded in orange. The units on the y-axis are labeled as number of kilowatts generated per day, and the units on the x-axis are labeled as number of days since power plant went online. The graph for this function also has the equation labeled next to this graph. It is y equals x raised to the third power, and the point 5,125 is also given because I can see on the y-axis we have that value 125 lining up with that point at x equal to 5. Okay, so for this problem we're going to do the same thing we did for 3a. We are going to need to find the units of that shaded region, and in order to find that we're going to have to multiply the units from the y-axis with the units from the x-axis. So I will set this up first as a multiplication problem of two fractions. So before I write down those fractions being multiplied, first I'm going to circle what we have here on the x-axis. We have 0 to 5, that interval from 0 to 5 on the x-axis, which represents the first 5 days since power plant went online. So we're going to need to know that for when we write down our final answer. All right, now we can write down the fractions that are getting multiplied here to figure out the units of what our shaded area represents. I'm going to write down number of kilowatts over day, and that's going to represent number of kilowatts generated per day times days over 1. The days are going to cancel out, and here we'll just be left with number of kilowatts. So I'm going to write this down as the total kilowatts over the first 5 days. And I'm going to box that answer in, and that's going to be what my shaded area represents. All right, so right now I would like to discuss how to use your calculator to evaluate integrals. And this is pertaining to the TI-84 Plus graphing calculator. So if you go to your math button on the TI-84 Plus, and I'm going to talk about like the TI-84 Plus CE first, and then I'll talk about the older calculator. We've got an older version. You want to press the math button first, and then you want to go to number 9. Number 9 option on that menu is going to say FNINT, and this will allow you to evaluate definite integrals. So you're going to want to press number 9, or you're going to want to make sure you get the cursor to land on number 9 and then press enter. And then what will appear on your screen, an integral will appear on your screen, and there'll be some like empty boxes that you'll need to be able to fill in. So you'll have an integral. You will need to fill in your lower limit, which will be like your a in this case, and your upper limit, which is your b, your function, which is your f of x, and dx, the variable to which you are integrating with respect to. All right, so I just wrote an arrow here, and this is the way it would look if you had an older version. It would say FNINT, open set of parentheses. You would type in your function, your f of x, a comma, x, the variable to which you're integrating with respect to, comma, then your lower limit, comma, and then your upper limit, and then close the parentheses and then press enter. So the one that's in the cloud is the one for the newer version of your TI-84 graphing calculator, and then the one in the second cloud after the arrow would be the one for the older version, what it would look like. And it will give you the same answer either way. Okay, example 4. The marginal cost function associated with producing pencil sharpeners is given by C prime of x, which is equal to 0.00006x squared minus 0.006x plus 4, where C prime of x is measured in dollars per unit and x denotes the number of units produced. Management has determined that the daily fixed cost in producing these pencil sharpeners is $100. Find A, the daily total cost for producing the first 500 units. I've gone ahead and I've circled daily total cost because that's what we're looking for, and I also circled first 500 units because that's also important. So we're going to have to find the integral from 0 to 500 of C prime of x dx. And this would be equal to C of x evaluated from 0 to 500, because the antiderivative of C prime of x dx is equal to C of x. So now that we have discussed how to use your graphing calculator to evaluate integrals, let's go ahead and practice on this problem. First, what we want to do is we want to go to the y equals button. That's the button that's in the upper left-hand corner of your graphing calculator, and we're going to type in our function. So that was going to be 0.00006 x squared, and then right arrow key to get out of the exponent, minus 0.006x plus 4. Let's go second quit to get out of that screen. And now we're going to go math. We're going to want the number 9 feature. So you're either going to press number 9, or you need to make the cursor land on number 9 and press enter. I'm just going to go ahead and press number 9. Here we have our integral, and we just need to fill in the empty boxes. Our lower limit for this problem is going to be 0. Now press the up arrow key. Our upper limit is 500. And then you want to press the right arrow key to get out of that upper limit. Go to vars and then go right arrow to y vars, number 1 to get that y sub 1. And then press that right arrow key to get in that dx part, and you want to press the x variable and press enter, and you will get 1,500. So that's going to be our answer for evaluating that definite integral. Let me show you another way you could do this. If we press the math button again to get that number 9 option, press 9. And we could still put in our upper limit and our lower limit exactly the same as we did before. So it's an integral from 0 to 500. And then when you do your right arrow key to get into the parentheses, instead of going to the vars button and pressing in y sub 1, you can also just go ahead and type in your function directly into this integral as the integrand. So I'm going to do that. So we're going to type in that 0.00000, 5 zeros, and then 6x squared, and then make sure you go back in the parentheses and press after the x squared, you want to go minus 0.006x, and then you want to go plus 4, and then right arrow key until you get to the dx part and type in that x variable and press enter, and you also get 1,500. So you could also do it this way and it would turn out perfectly fine. So that is our answer for that definite integral that we just did for our problem. Let's go back. So we're just going to write here, this is equal to, and remember to write down that dollar sign because we are talking about money, $1,500. This represents the daily total cost for producing the first 500 units. B, the daily total cost for producing the 201st through 400th units. So this is going to be the integral of 200 to 400. So our lower limit is 200, our upper limit is 400 of c prime of x dx. And this is going to be equal to c of x evaluated from 200 to 400. And once again, we can go ahead and just do this on the graphing calculator and it will give us that answer because it allows us to evaluate definite integrals. I'm just going to go ahead and write down the answer because I already showed you how to do that on the graphing calculator, so you could do that on your own. This will be $552.